Kalman Filter is an algorithm that produces estimates of state variables for a discrete data control system. The Kalman algorithm boils down to these set of 2 predict and 4 update equations. A system is fully described by matrices F, B, H and Q. Xk are the state variables, Uk are the controlled inputs and Zk are measurements. The job of the Kalman filter is to produce estimates for state variables given the measurements, the initial state and the system definition. There are several types of operations involved in computing the outputs, namely matrix vector and matrix-matrix operations. The order of operations of computing one set of outputs comes out to be around 13n cubed. For a 6-dimensional matrix, this is in the range of kiloflops. For real-time applications, one must finish in millisecond range, which implies a throughput of around 5 to 10 megaflops. Analyzing the DAG for this computation gives us several ideas of possible optimizations. There are 6 parts to this computation, namely state predictor, measurement residual, covariance predictor, Kalman gain calculator, and the state update and covariance update. We can see that the left branch is independent of the right branch and thus can be parallelized. This gives the scope for a few possible implementations, but we shall present 3 implementations, namely baseline C, multi-threaded using OpenMP, and custom hardware using Bluespec and Vitis HLS.
We initially implement a single-threaded C implementation of Kalman filter, which will be considered as the baseline for further analysis. We try out a couple of profiling tools on the C implementation to understand the bottlenecks of the system. We perform profiling of C code using Valgrind. Valgrind is a simulated virtual machine. Valgrind's profiling tool is used to analyze the code with the output being shown in the K-cache grind. As we can see here, the total number of instructions executed is around 4 lakhs. Now, implementing this and visualizing the profiling result using K-cache grind, we arrive at the following. As we can see, the Kalman gain calculator, covariance predictor and the covariance update are the time-consuming functions. The other 3 equations, state update, state prediction and measurement residual, are not shown in the call graph since they are negligible in computation time compared to these 3. We can also see that the most amount of time is being spent on matrix multiplication. Thus, for reduction in time, the matrix multiplication operations must be optimized, and if possible, the 3 equations, Kalman gain calculator, covariance predictor and covariance update in the call graph must be parallelized. But since the equations are dependent on each other, they have to be executed sequentially. They can't be parallelized for the same iteration. We tried out other profiling tools like gprof and Google performance tools as well. gprof and Google perf tools are sampling based tools. The output from these tools can't be used for analysis because the system is being undersampled because of low sampling rate.
For multi-threading the C code, we use OpenMP directives. Let's look at the timing results we have got for 100 iterations. So here we have the result for normal C code. It takes 0.014 seconds, and this is the result for OpenMP, and this takes 0.0056 seconds. It's much faster, right? And now let's look at the code now. This is the part where we have parallelized using task parallelism. Using task parallelism, we can achieve softer pipelining and tasks are generated for the 2 branches of the DAG. When we have executed tasks in a for loop, they get stored in a task queue and the original code continues to execute the for loop while the other free codes execute the task stored in task queue. We can extend the parallelism to all parts of the algorithm, but the overheads of synchronization was the lowest for this particular set of tasks and it gave these results. This result is obtained by profiling through Valgrind, and as we can see from the graph, the task is getting generated here and the original code continues executing the Kalman iterate for loop while the other code executes the task.
We now present a Bluespec implementation. We chose Bluespec over Verilog because of a few reasons. The first being ease of use. One can directly map the task schedule to hardware description using Bluespec's rule-based approach, so it is easier to write sophisticated state machines. Second, more control. It is closer to the hardware description than Vitis HLS and offers more control over architecture, clock cycle counts, and latency. Third, library support. we made use of the fixed point library of Bluespec. We have used the configuration fixed point 16,16 in this project. There are three major operations involved: matrix multiplier, vector dot product, and matrix inverse. We shall now describe these architectures. For matrix multiplication, we choose a systolic array based architecture. The inputs are fed as streams into the multiply accumulate processing elements. It takes a total of 3n minus 2 clock cycles, where n is the dimension of the matrix, to compute the product, a significant improvement over the O of n cubed in single-threaded implementation. For matrix inverse, we explored several architectures such as QR and LU decomposition, but finally we ended up going with Gauss-Jordan elimination using row operations. Each clock cycle, one column becomes a pivot by subtracting the pivot row multiplied by the ratio of a pivot element and the element in the row from that row. A complication arises when the pivot element is 0. This is when you are supposed to switch that row with the non-zero element row, but this would have taken a lot of control logic. Instead, if we just add all the rows below and including the pivot row, we get around the problem of choosing a non-zero row. Finally, each row is divided by the pivot element, and performing these same row operations to the identity matrix will result in the generation of the inverse matrix.
The vector dot product module is a pipeline module used for computing dot product of two vectors. It takes in three inputs: an element of vector A, an element of vector B, and a boolean value to indicate whether the element is the last value or not. In our Kalman module, we use the vector dot product module to compute matrix into vector operations. Now let's look at how the synthesis comes out for the Bluespec module. So as we can see here, the Bluespec code has the Kalman module has ports uses a lot of ports, and this cannot be synthesized. So hence we need to write a top module. So we have made a simple wrapper module which feeds xk, pk, and yk. So they feed these values to the Kalman module, and the output is stored back into registers. Wrapper module also requires a top module because we need to configure the file for the required FPGA. Our targeted FPGA is the Kintex 7 and which has the advantage of 110,000 LUTs. The top module is a very simple file, and the main function of the top module is configuring the clock. Our Kintex 7 FPGA uses a differential clock, so we need to use the clock wizard for configuring the clock. The results of implementation and synthesis are as follows. The maximum clock frequency we could achieve in this FPGA is about 8.5 MHz.
Initially, the baseline C code was modified and synthesized using Vitis HLS with reduced optimization. When synthesized and simulated, latency of around 370 clock cycles was observed. Then run at a frequency of 20 MHz. The maximum clock frequency estimated was around 32 nanoseconds. This alone provided a speedup of around 12 times when compared to a single threaded C code. The implementation was done using floating point operations. Moving forward, we made further optimizations to the base HLS implementation. All the matrices were completely partitioned into individual registers, which allowed us to unroll to a very large extent, thereby providing very high speedup. The addition and subtraction of matrices and vectors were completely unrolled. Since matrix multiplication and division operations take up significant resources, they were partially unrolled. Functions were inlined to reduce the overhead while jumping between the functions. Loops were made perfect or semi-perfect to flatten them, thereby reducing the enter and exit overhead. After significant hardware optimizations, following results were observed. We were able to get the latency to 97 clock cycles with 20 MHz clock, with the maximum possible clock frequency of 32 MHz. This results in a speedup of around 46 times. Moving forward, the HLS code can be further improved by pipelining the functions themselves. Currently, only the loops are pipelined. Instead of Gaussian elimination, the inverse of matrix can be performed through other means like QR and LU decomposition, which might be more hardware friendly. In comparison to Bluespec, Vitis HLS is much easier to generate the hardware for DSP based algorithms based on our experience. It is also much easier and faster to generate the hardware, thereby reducing the time to market.
The main problem with HLS is that it is difficult to understand how the hardware is generated by the code, and this is very important from a designer's perspective. This is also a major concern if we would like to reuse standard implementation modules for which ASIC synthesis has been analyzed already. I would also like to mention some of the reasons why the Bluespec code didn't perform as expected. So these are the possible places which we could improvise. So one is the systolic matrix multiplier can be pipelined easily, and the data can be fed in and the result can be got out in the form of streams. This has not been utilized in our implementation, and for ease of coding we have used some more buffer stages which adds to the total resources utilized. We also need to analyze other implementations of Kalman algorithm to reduce the resource utilization in our Bluespec code. The third improvement which is possible in our Kalman module is the feeding of inputs. So the matrix module PK can be fed in the form of streams, and the vector modules XK and UK can be fed element wise, which is suitable for the first operations.
So at the end of the day, we have three different implementations. We have the baseline C++ synthesized in HLS. We have HLS after several modifications and optimizations. And we have Bluespec synthesis for FPGA Kintex 7. We have also synthesized the HLS versions for Kintex 7. And let us compare all three implementations using a Pareto optimality chart. The two parameters we have for our Pareto optimality chart are resources consumed, as in the logic cells for the Kintex 7, and the speedup obtained. So we start with the Bluespec implementation, which gave us a 5.8x speedup and consumed around 33,000 logic cells. Then we have the baseline HLS, which consumed around 17,000 logic cells and gave us a speedup of around 12 times. This easily dwarfs our Bluespec implementation. And finally, we have the optimized HLS, which provided a speedup of 46x and has only around 10,000 to 13,000 logic cells. As we can see, HLS blows Bluespec out of the water. We have also discussed why Bluespec did not perform as expected. So the conclusion is, HLS is a good tool for such DSP applications, and Bluespec offers more control and has some advantages, but unless a lot of lower level optimizations are exploited, it is very difficult to get a good speedup and a less utilization compared to HLS using Bluespec. So that was about Kalman filter. Thank you.